Dear students, welcome back to our online certification course on analog electronic circuits. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion, it is multi-stage amplifiers, rather continuation of multi-stage amplifier. And in the previous three lectures, what we have seen is the theoretical aspect of going for multi transistor amplifiers, where we do have mixed configurations, namely CE, CC and so and so. Today, we are going to discuss little more about numerical problems and demonstrating the same conclusion what we have discussed theoretically. So, as I said that our according to our overall plan, we are at multi-transistor amplifiers and theoretical parts of CE, CC, then common source, common drain, then common collector, Darlington pair. Those configurations it has been discussed from the circuit analysis point of view. And today we are going to have more numerical problems. So, here again the same summary here, the concepts we already have covered, particularly the theoretical aspects of mixing different configurations are covered, and we are going to discuss about numerical examples of particularly for CE followed by CC. Common collector stage, to enhance the bandwidth of the amplifier. And so, similarly for MOS counterpart, common source followed by common drain, it gives enhancement of the bandwidth. So, these two configurations are for bandwidth enhancement. And the third example, it is to demonstrate that increase of input resistance R in. So, compared to CE amplifier, whatever the input resistance we have seen, here we will demonstrate that if you precede this circuit by common collector stage, the input resistance it is getting increased. So, let us go to the numerical example. So, this slide is recapitulation of one of our previous numerical examples, where we have discussed about CE amplifier having fixed bias arrangement, and different parameters are given here, including the supply voltage of 12 volt, then device parameters including beta of the transistor, early voltage, then VB on, and then also we do have the bias circuits resistances are given here, RB, and then collector resistor and so and so. And the coupling capacitors informations are also given, and then the device intrinsic capacitances, namely C pi and C mu are given here as so this is C pi as and its value it is given 10 picofarad, and C mu it is 5 picofarad. And based on that information, what we have done is that we obtain operating point. So, just for your information, I will repeat some part of it, and then we will see that how enhancement can be made on this one. So, let us try to see the operating point of the transistor. So, whatever the arrangement we do have here, namely the fixed bias VB, and then VB at this node, essentially the VCC it is directly coming to the base node through this RB. And if I consider the KCL as you may recall, KCL from supply voltage to ground and the drop across this RB, then VBE drop, we can get the expression of the IB, and then we can get the numerical value of the IB. So, we can say that VCC minus VBE on. So, that is equal to IB multiplied by RB. So, that gives us IB equals to VCC minus VBE on divided by RB. So, its value it is now 12 minus 0.6 divided by RB, it is given as 570 kilo ohm. So, that gives us the IB current of 20 microampere, and then using this information and the beta information, we are getting the collector current, which is equal to 2 milliampere. Now, with this information we can find the value of the small signal parameters, namely GM. In fact, let me complete this part and then I will be coming to the small signal parameters. So, we do have IC equals to 2 milliampere, then drop across RC equals to 2 milliampere multiplied by RC, it is 3.3. So, that gives us VCE equals to 12 volt minus 3.3 into 2, which is 5.4 volt. So, the operating point it is given here, and based on this operating point we can now calculate the small signal parameters value, namely GM equals to IC divided by VT, and this is 1 by 13 mho, and then the R pi, which is beta divided by GM. So, that is equal to 1.3 kilo ohm, and then R naught, it is VA divided by IC. So, that is equal to 100 divided by 250 kilo ohm, and from that we can get the voltage gain. So, now we obtain the small signal parameter, now we can get the voltage gain. So, voltage gain it is GM into RC in parallel with R naught. So, the GM we have 1 by 13 and RC it is 3.3 K in parallel with 50 K. So, probably you can approximate this by 50, or probably you can calculate this parallel resistances together, and then you can find what is the output resistance. So, that is coming close to 3.1 in my calculation, it is 3.1. So, that gives us 3.1 K divided by 13. So, that is 230, yeah, in my calculation it is 238. So, that is the gain we are getting. Now, next thing is that we can find the lower and upper cutoff frequency. So, this is the the exact statement of the problem we have addressed earlier. Now, for our main focus to demonstrate how the bandwidth it will be extended, we can probably calculate only the upper cutoff frequency using whatever the information we do have, and you may recall the upper cutoff frequency, it is considering whatever we do have here. So, upper cutoff frequency, let me use this space, its expression is 1 by 2 pi then R out of this stage multiplied by whatever the CL we may be having, and the value of the CL it is given 100 picofarad. So, that multiplied by CL, and this resistance if I call R O, let me call this is R O, and we already have done this calculation of this R O, which is 33 kilo 3.3 kilo in parallel with R O here. So, the value of this upper cutoff frequency can be obtained by considering that 3.1 K multiplied by 100 picofarad, which is 10 to the power minus 10, and that gives us I have done the calculation for you. So, this is coming 513 kilohertz. So, in summary, what we have circuit performance wise, we do have the circuit gain is 238, and then the upper cutoff frequencies 513 kilohertz. Now, the exercise we are going to do, it is that we are going to put in this case, instead of putting the capacitor here, we can probably directly put a CC stage here, and rest of the things we will be keeping same, and then we will see that how this the bandwidth, particularly bandwidth is getting extended by putting the CC stage there. So, in the next slide we do have the CE followed by CC, and the information about all these biases are maintained, namely R1 earlier it was RB, and then R2 it is actually the RC of the first stage, and then we do have the CC stage. So, the CC stage it is this has been added here, and the value of this resistance, its bias circuit, it is given here as 1.2 kilo ohm, and the C1 and C2 we are keeping same. C1 and C2 it is 10 microfarad, and then CL, instead of connecting the CL at this node, we are connecting the CL after the CC stage. And to get the overall gain starting from the primary input to primary output, first of all this part we already have done, and we have seen that its gain it is, if I call AV1, its gain it is 238, and then its output resistance if I call RO1, which is 3.1 K, and then yeah. So, these two informations are important, and then to get the overall circuit performance we need to see what is the small signal parameters we do have out of this CC stage. But to get the small signal parameter, we need the operating point of this Q2. So, how do you find? We know that DC voltage coming here, it is 5.4 volt. In our previous analysis we have done that. So, if I say that we do have 5.4 volt DC, so that is 5.4 volt along with its Thevenin equivalent resistance, which is R O 1. So, that is 3.1 kilo ohm. That is coming to the base of transistor 2, and the transistor 2 emitter of transistor 2, it is connected to ground through this R 3, and R 3 it is 1.2 kilo ohm. So, this is our output, and this node it is connected to the supply 12 volt. Now, if I analyze this circuit, and again if I consider the device parameter same as Q 1, namely VB, beta and early voltage, it is same, and then analyzing this loop, what we can get is the value of the IB, value of the IE, and so and so. So, you may ignore the drop across this resistance due to flow of IB. So, you can say that this 5.4 volt it is directly coming to base. So, we can say that VB 2 it is approximately equal to 5.4 volt, and then we do have 0.6 voltage base to emitter voltage, and then we can see what is the voltage here coming here. The voltage DC voltage coming here, it is 4.8 volt. So, that is the emitter voltage, and that gives us the current flow through transistor 2, which is 4.8 divided by 1.2. So, we can say that the emitter current it is equal to 4.8 divided by 1.2. So, that gives us 4 milliampere of emitter current, and we may approximate that the collector current it is also equal to emitter current. So, IE 2 equals to 4 milliampere. So, using this information, what we can get the small signal performance parameter, namely GM2. So, the GM2 it becomes IC divided by thermal equivalent voltage, which is equal to 4 divided by 26, that means 2 divided by 13 mho, and the R pi 2. So, that is beta divided by GM. So, that is equal to 650 ohm. Okay. So, you might have observed that the R pi here and R pi here, they are different because their current levels, collector current levels, they are different. Now, using this we can find what will be the gain of the CC stage. So, what is the expression of the gain of the CC stage? If I call this is AV2 gain, voltage gain of the second stage, if of course, it will be very close to 1, that is the anticipation, but to get precise value you may recall its expression, it is 1 plus beta into the resistance here. In fact, you may ignore R naught. So, of course, this R naught it is 25 kilo ohm, and this 25 kilo ohms you may ignore compared to whatever 1.2 kilo ohm we do have, and then the expression of the voltage gain, it will be 1 plus beta multiplied by this R 3. In fact, this is in parallel with R O 2, which can be ignored, and then 1 plus beta 2 multiplied by R 3 in parallel with R O 2 plus R pi 2. Yeah. So if I consider we do have a signal at the base and how much the voltage it is coming here, that can be obtained by considering this. You may recall that this equation, in case if you are unable to really intuitively get a feeling of that, you can think of that we do have R pi here, and at this point we do have an impedance coming from this resistance seen from the base, and this resistance it will be seen at the base after multiplying with 1 plus beta, and this resistance of course we do have R naught 2, it is coming in parallel. So, beta plus 1 into R 3 in parallel with R O 2 is essentially the resistance at this emitter, and effect of this emitter rather seen at the base. So, whatever the impedance we can see here from here to here, effective impedance seen from the base, it is 1 plus beta times the corresponding resistance. But anyway, you can consider their numerical value, and so this is 101 multiplied by 1.2 k, and then we do have 101 into 1.2 k plus R pi 2, which is 0.65 k. So, that is giving very close to 1. In fact, I do have the calculation for you. It is coming 0.995. So, we do have the first stage gain here, and then we do have the second stage gain. So, the overall gain, so we can say the overall gain A V overall equals to A V 1 multiplied by A V 2, and also of course, we will be having some attenuation due to the loading effect coming there. So, we will see this part. So, what will be this part? It is the impedance at this node, essentially it is loading the first stage. So, this factor, whatever the question mark we are saying here, let us try to see that part. It is the attenuation coming due to the loading effect, and the load here it is the R pi 2 plus 1 plus beta into R 3, and that is loading the first stage, which means I have to consider output resistance of the first stage. So, this divided by R pi 2 plus 1 plus beta into R 3 plus R O 1. So, this is the attenuation factor. So, that factor if you put it here, in fact, if you put the value here, whatever the value you will be getting, this factor it is approximately coming very close to 1. In my calculation, it came 0.975. So, I should say that the overall gain it is 238 multiplied by A V 2, which is 0.995, and then multiplied by 0.65. 975, and that is coming very close to the original gain, and it is, in my calculation, it comes 131. Okay. So, there is a change, but the change is very small as anticipated. Now, next thing is that how the CC stage it is enhancing the bandwidth. So, how do we calculate the bandwidth? First of all, we have to see the corresponding GM, and then we have to see what is the corresponding impedance coming there. Namely, we need to calculate what is the RO coming from the CC stage, namely RO2 we need to find, and then we can find what is the corresponding cutoff frequency defined by this RO2 and CL together. And then also we do have another candidate to define the cutoff frequency, that whatever the input capacitance we do have coming from the second stage multiplied by whatever RO1 we do have. So, to calculate the upper cutoff frequency, we have to consider these two time constant. Okay. So, I will be using the same slide. So, let me clear whatever the clumsy equation now we have created. Yeah. So, let you consider the output resistance here. So, if I call this is RO2, ideally if this node it is AC ground, then RO2 should be equal to 1 by GM2 in parallel with R3 in parallel with RO2. So, that we may approximate by 1 by GM2, and that is 13 by 2, that is 6.5 ohm. But then this is not possible, we cannot do the AC ground here. So, we have to consider the corresponding resistance here. In fact, for the CC stage, we have to consider that the resistance at the base, and this resistance is RO1, right. And then we have to see what is the corresponding output resistance we do have. That can be obtained by considering the drop it will happen across this R pi in presence of the RO1, while we are say stimulating this circuit by say Vx. So, I should say if I am applying Vx at the emitter, then base to emitter voltage it will not be exactly minus Vx. As a result, whatever the internal current source, namely Gm into VBE. So, this VBE part it will not be entirely coming from minus Vx, rather this Vx it is having some attenuation here. So, what is the attenuation coming due to this RO1, which is unbypassed, that is R pi divided by R pi plus RO1. And in this case, so I have to consider R pi 2, this is R pi 2, and then of course, if I multiply with Vx, so that gives us minus Vb. So, whatever the expression we obtained for this RO2, assuming that its base node it is properly getting grounded, that need to be changed. So, what is the changed output resistance? RO2 should be 1 by GM2 multiplied by this attenuation factor. So, that attenuation factor it is R pi 2 divided by R pi 2 plus RO1. So, now we know the value of different parameters. So, we do have this is 13 by 2, and then R pi it is R pi it is 0.65 kilo, and R O 1 it is R O 1 earlier we have calculated it is 3.1 K. So, if I consider the 3.1 K and 0.65, 3.1 K, and that gives us the different value of this R O 2, and I do have this calculation for you. It is coming 36.36 ohm. So, note that this is different, but still it is quite low, and the pole it is getting created by this R O 2 and then this C L. So, that gives us the new upper cutoff frequency. So, if I call this is F U dashed, and if you find what will be its value, it is 1 by 2 pi into this R O 2 into C L. So, that is becoming 2 pi into 36 into 10 power minus 10 farad, and in my calculation what I was getting here, it is 43.75 megahertz. So, now you may recall this is you can compare this value and previously obtained upper cutoff frequency. Originally it was F U, that was 513 kilohertz if we consider only this circuit, and then if we connect the C L here, then the bandwidth or the upper cutoff frequency it was this one. But of course, this is not the only candidate to define the upper cutoff frequency. You also have to see that what is the F U we are getting due to this R O 1 and the input capacitance coming from this stage. And what is the input capacitance? We do have C in 2 equals to C mu, and the value of the C mu it is given here, it is 5 picofarad. So, the I should say intrinsic or I should say device capacitance of say 5 picofarad, and then R O 2 which is 3.1 K, they are providing the other possible option of the upper cutoff frequency. In fact, not only you have to consider R O 1, you have to consider the input resistance of this circuit also. So, at this point, let me use different color here. At this point, whatever the pole will be getting, it is coming from we do have R O 1 and then R in of the second stage, and then we do have the capacitance coming from the second stage, which is C in 2. So, I should say these two resistors, they are coming in parallel to define the corresponding R. So, the new candidate or the other candidate to define the upper cutoff frequency, let me call it is F U double dashed, and so this is equal to 1 by 2 pi, then 3.1, and we do have the this resistance. Of course, that resistance we have calculated, but somewhere we have missed it. And what is its expression? It is R pi 2 in series with 1 plus beta times R O 2. So, you may ignore this part, but even if you consider this, the corresponding resistance here it is coming very close to R O 1. So, you can consider this is R O 1 multiplied by, now it is 5 picofarad instead of having 100 picofarad of CL. Now, we do have only 5 picofarad seen by this resistance, and this is 5 into 10 to the power minus 12, and its value incidentally it is coming 10.6 megahertz. So, I should say, even though we do have now two candidates to define the upper cutoff frequency, one is FU double dash and also we do have FU dash. So, these two if I compare, this is lower. So, eventually this is defining the upper cutoff frequency, but still if I compare with the original upper cutoff frequency, this adding this CC stage, it is helping us to extend the bandwidth. So, in summary, we can say that if the original CE amplifier it is having a frequency response like this, so it is having a gain. So, this is AV 1 in dB and this is frequency in hertz in log scale, and this one was 513 kilohertz was the upper cutoff frequency. Now, by adding this CC stage, what we have here it is the gain got slightly decreased, but then bandwidth got extended, and this bandwidth it is 10 megahertz. So, almost 20 times enhancement of the bandwidth, and this is due to, so this is due to the CC stage, in fact CE and CC together. Okay. So, let me take a short break and then we will come back for the MOS counterpart, and then we will see that there also by using common drain stage how it is helping us to extend the bandwidth. Okay. Thank you.